Alright, our last lesson on transformations is what we call inverse relations or inverse functions. So our in our last topic we looked at horizontal and vertical reflections, and then we did diagonal reflections. Today we're just going to examine the diagonal reflections a little bit more in detail. So when you look at this graph that I've got on the title page, you can see it is a diagonal reflection. Our blue graph is diagonally reflected across the y equals x line. You can see our notation is slightly different. When we wrote this yesterday, instead of it being y equals f of x, we write it as x equals f of y. So this inverse notation we haven't introduced yet. And that's where we're going to start. We're just going to look at different notation, figure out how to do the equations. We didn't actually solve the equations previously, and then we're going to look at a few domain and range issues that pop up. So first off, we're going to look at our notation. So typically when we talk about a diagonal reflection, we had said our equation y equals f of x changes to x equals f of y. So we're just trading our x and y coordinates. That's still true, but we're just going to introduce another notation as well. So instead of writing it as x equals f of y, often we just use f to the negative 1. So that stands for the inverse of x. Be careful, the negative 1 is not an exponent. It's not like x squared or x cubed or something like that. The negative 1 in this case is telling us to do an inverse. And it's very similar, you guys might remember from trigonometry, when you solve something like sine of x equals 5 over 8 on your calculator, you would type it in as sine inverse 5/8, and that would give you the x value. So the inverse function is kind of like undoing it or doing the reverse direction. So in terms of the graph, the inverse function graph is exactly the same as the diagonal reflection that we did earlier. So because it's just getting reflected across that y equals x line, it is just a flip of the coordinates. So you can write it either way. You can write it as x equals f of y, or you can write it as f inverse. They're both the same. They both do the same thing. The diploma expects you to understand both, so we have to sort of be familiar with the two different notations. So one thing that we looked at in the previous lesson, I gave you an equation, something like y equals 3x minus 2. So we said the diagonal reflection equation was x equals 3y minus 2. We just trade the x and the y variables. So that's still true, but the problem is we can't actually graph that. So the top one, the original, you can put that in your calculator and get that graph. So our graph would just be a straight line. The second one, we can't get the graph. So often what we want to do is actually figure out what the inverse equation is as a function of x, not as an x equation as a function of y. So we need to know how to switch these equations around. So you can see, if I gave you, let's just do this one as our first example. So if our original equation was f of x equals 3x minus 2, the first thing we want to do is change it to y equals, just to make it a little bit easier to solve. So we write it as y equals 3x minus 2. Then do our diagonal reflection, so switch our x and y around, so we'll let x equals 3y minus 2. Now we just solve the equation for y, just like you do any other equation. So if we bring the 2 over, we have x plus 2 equals 3y, and then we could divide by 3. So we have y equals, and let's just write it as a fraction, 1/3 x plus 2. And our last step typically is, because we started with an f of x function, let's just rewrite it as f inverse. And we can leave it as 1/3 x plus 2, or you could even FOIL it out if you want. So 1/3 times 2 would give you 2/3. So now when we graph this, it should work. If we were to graph our original, let's fix the graph here a little bit. Okay, so if we graph our original, it should have been a straight line, something like that. Now if we graph the inverse that we just figured out, 1/3 x plus 2/3 would be a line something like that. And you can see, if we put in our diagonal line, it does look like they are a diagonal reflection of each other. Okay, so let's do another one. This one's another linear type of graph. So our first thing, remember, this is f of x, so let's rewrite it as y equals. Then the next step is flip our x and y around. So now we've got the diagonal reflection equation. Now we want to solve it for y. So let's bring the 3 over,
that'll be plus 3 equals the 3/5 y, and then let's divide by 3/5, or because it's a fraction, it's a little bit easier to multiply by 5/3, and that will undo the 3/5. And again, our last thing is we should write it as an inverse, and let's just flip our order around, so we'd have 5/3 x, and 5/3 times 3 would be just 5. And we're done. So again, you could always graph the original, which would be a graph something like that. Graph our new one, which would be 5/3. Usually graph maybe something like that, and where they would cross. I don't quite have my graphs right, but where they would cross, somewhere way up there, should be where our invariant point would be. Okay, so what we have to be careful of is, because we're dealing with functions, I'm just going to go back to this previous one, because our original was a function and our inverse is also a function, we have to actually make sure that they are indeed functions. Because these are both just linear lines, they're fine. So our original, domain, and range of the original would just be any real number for both. And our new one is also a straight line, so its domain and range is also any real number. So we don't have any problems with this one. But with other graphs, like quadratics and things like that, we will run into situations where the inverse may or may not be a function. So remember, when we're dealing with functions, we can only have one y coordinate for each x coordinate. And the easiest way to sort of see if something's a function or not is if it fails the vertical line test. So if we have like a straight line, it doesn't matter where we draw a vertical line, it's only going to cross once. So that's a function. If we have a quadratic, something like that, again, it's only going to cross once if we draw a vertical line anywhere. It's also a function. But if we had a quadratic that was sideways, you can see now that if we draw a vertical line, it's going to touch in 2 spots. So that one would not be a function. So because we sometimes get things that aren't functions when we do inverses, we have to be really careful for domain and range, and often we have to change the domain or range in the original to make sure that it actually works for the inverse. So let's look at a quadratic. This one is one that's going to show us that we have an issue. So again, we want to solve it first, so let's just rewrite it as y equals, and then now let's do the inverse. So let's flip our x and y around to get our diagonal graph. Now we want to solve it for y, so when we bring the 1 over first, and we have squares, we want to undo that, so let's square root both sides. We'll get rid of the squaring, and then our last step is we want to bring the 3 over. So we have square root of x plus 1 minus 3 equal to y, and we're done. So that should be our inverse function. So square root x plus 1 minus 3. So now this is where we have an issue. If we were to look at the original graph, so our original, let's rewrite them on the next page here. Our original was x plus 3 squared minus 1. Okay, so let's sketch that one first. So that one will be 3 left and 1 down, so it'll be something like this. So we should have a quadratic that looks something like that for our original graph. So if we just do our diagonal reflection, let's kind of sketch that in first before we look at our actual inverse equation. So if we do our diagonal reflection, this coordinate that's at -3, -1 is now going to be -1, -3. It's going to go about there. And these two would switch to here, so we'd end up getting our quadratic would look sideways like that. But you can see that's no longer a function. So what happens is when we do our calculation of the equation, let's go back to the previous page, our inverse is square root x plus 1 minus 3. So if we were to graph that on our calculator, what actually ends up happening is the bottom part of the graph does not show up. So our calculator only draws the top part of the equation. So it looks something like that, like this whole bottom part is now gone. But that makes sense because It's the bottom half that makes this thing not a function, and your calculator can only sketch out functions. So our inverse equation is only half of the original quadratic. So let's figure out what the domain and range is of the inverse. So our domain of the inverse is greater than -1, and our range, you can see, is greater than -3. So if we kind of compare that to our original function, we had a domain of any real number, and our range was greater than -1. So because, remember, when we're dealing with diagonal reflections, our x's and y's trade, so that means our domain and range would trade. So our range is good. You can see our range of greater than -1 matches our domain on our new function. That part's good. It's the range that is at -3 to infinity that should match our original domain, which it doesn't. So what we have to do is change the original to match that. So our original should be from -3 to infinity. That'll match our domain and range issue, but that also means then we've actually changed our original graph. So our original function, that quadratic iterative function, we only want to go from -3 to infinity, so that means we're going to eliminate the whole left hand of the graph. And by doing that, we now solve the function issue. So the original half of the quadratic is still a function. It reflects into our inverse, which is still a function. Everything's good. So that tends to be the best way to solve these questions, is graph the original, do your equation of the inverse, figure out the domain and range of the inverse, and then go back to the original to make sure it matches in the opposite order. Your domain and range must get flipped to make it match. And that's it. So once you do that, everything's good. So the other option is we could have split the original equation as the negative, right? We just did the positive part of the functions. But we could have, if we wanted to, we could have done the original negative side, but that would have matched the negative square root. So in most cases, it's easier to stick with the positives, but it would work exactly the same if we did the less than -1 and 3, not greater than. Okay, so just to kind of remember, if we don't get a function, we have to be careful. You want to figure out the inverse, and then once you have the domain and range of the inverse, you want to make sure the domain of the range of the original will match that. And we won't bother about this because it's just more of the same graphs. So that's it. We've got everything taken care of. So solve the original, do the inverse, figure out the domain range, and then work backwards. And that's it. Maybe let's do one new one on this last graph page since I've got a grid. Okay. So let's suppose our original is just y equals, let's do an absolute value. Let's go absolute value of x plus 4. So let's sketch that one in. So that will be our original graph. So if we do our inverse, so if we actually were just to work with coordinates, so this original coordinate is 0, 4, so that would become 4, 0. And if we do our diagonal reflection, our graph would end up looking something like that. So it is a diagonal reflection, but again, we have the new inverse is no longer a function. So what we want to do is restrict our domain and range. So let's only do half of the original, or sorry, half of the new one. So let's do the domain and range of that one first. So our domain of this new graph is greater than 4. And our range is greater than 0. So that means our original had to match that as well. So if we make our domain of the original greater than 0, and our range then would be greater than 4, right? Because those have to match. So if we go back to our graph, so if our range is greater than 4, that looks okay. Our domain of greater than 0 then would only be the positive half. It would look something like that. And that's it. So we won't worry about solving the equations, because solving an inverse of absolute values, the equation gets a little messy, but I just wanted to show you the whole process of draw the original, draw the inverse, do the domain and range of the inverse, work backwards to fix the domain and range of the original. And that's all for inverses, and that's it for our whole transformations first unit.